Welcome to another Ultralight Airplane Design video from the Ultralight Airplane Workshop. This is a continuation of the UWS-4 Aerodynamic Design series. And in fact, this is a continuation of a little mini-series. This is part 13B. And by the way, I should mention, we're working on an ultralight airplane that meets the FAA, Federal Aviation Administration, Part 103 regulations. Now, in the last video, part 13A, we figured out where the neutral point of our airplane was, basically the aerodynamic center of the whole airplane. And then we figured out what the static margin is. We wanted to figure out what the pitch stability of the airplane was, and that's the static margin. So the bigger that number is, the more stable the airplane is in pitch, and the safer it is to fly. Now, part of figuring all that out was how big the tail should be, and also how far back behind the airplane the tail should be. Well, there's another thing we need to think about on the tail size, and that's when we're at our worst case condition for that tail to have to push down. Now, generally, that's when you're going to have a forward CG. So in this video, we're going to examine that. We're going to look at our worst case scenario and figure out how big a tail do we have to have in order to counter this worst case forward pitching moment of the airplane. In this video, I'm going to be using a lot of terminology that is commonly used in aerodynamics, but maybe you're not familiar with it, or maybe you need a little refresher. If that's the case, I'm going to put a link up here in the upper right-hand corner that you can click on. That will take you to a playlist that I've made of definitions and explanations of various aerodynamic terms. So feel free to go take a look at anytime you use a term that you're not familiar with. And by the way, I do mention other videos here in this video. And so whenever you see a little box appear up here in the upper right-hand corner, that'll be a link to the video that I'm talking about. So if you're curious and want to see it, go ahead and click on that. Now, as I said in the last video, we were looking at neutral point and static margin. And we used Dan Raymer's book, Simplified Aircraft Design for Homebuilders, to give us the equations we need to do that analysis. Dan doesn't really cover what we're going to talk about in this video, so I have to use some other resources for that. Now, one of them is Modern Aircraft Design by Martin Hallman, and I don't think you can get that book anymore. You can probably find it used, but I don't think you can get it new anymore, so I don't have a link for this book. And the other book is Aircraft Design, A Conceptual Approach, and that's by Dan Raymer. So he's the same one that wrote Simplified Aircraft Design for Homebuilders. It's just a much bigger book. It's a textbook, got about 1,000 pages in it, and it's in its 6th edition. I don't think I have a link for that book either, but you can find it on Amazon. And as a quick reminder, this video is not a substitute for any of these books here. If you really want to use the information that's in this video, you really should go look at those books because they can give you far more in-depth information. And I do have a link in the description down below that'll take you to the Ultralight Airplane Workshop book page, and there are links to Amazon there where you can buy other books that I found very useful. And if you do use one of those links to buy one of those books, the Ultralight Airplane Workshop will get a small cut of that because those are Amazon associate links. Let's do a real quick review of what we did in the last video and compare that to what we're going to do in this video. In the last video, we wanted to find out how to keep the airplane stable as we moved the center of gravity on the airplane back. Or even on some airplanes, like high-wing airplanes that are tractor configuration, maybe you don't have to worry about moving your CG back. Maybe your pilot's center of gravity is right underneath the 1/4 mean aerodynamic chord. Maybe your fuel is also centered there. Maybe anytime you throw baggage in your airplane, it's also centered there. So maybe your CG doesn't actually move away from that 1/4 mean aerodynamic chord. Well, the neutral point of the airplane has to be far enough back from where that CG is that the airplane is going to be statically stable. In other words, if you're in trim flight and it gets somehow disturbed and the nose pitches up or down, it'll return to level flight again. And it'll do it fairly rapidly. So that's an airplane that's stable in pitch, and it's fairly safe to fly depending on how big that static margin is, the difference between your CG and your neutral point. So we calculated where the neutral point was based on where I thought I would have my tail. And so there's this length right here, that's a lowercase l, there's this length here from the 1/4 mean aerodynamic chord to the 1/4 mean aerodynamic chord of the tail. Now, I already had a surface area for that horizontal tail figured out, and we did that using the volume method. So what I want to do is verify that that was a reasonable surface area, and this length was reasonable when you combine them together to move that neutral point far enough back that I had plenty of static margin. And we used Dan Raymer's book to figure out how to do that. Now, I don't remember the exact numbers. I think the static margin we ended up with was a little over 7, because our neutral point was back around 39% of the chord. And with the static margin of a little over 7, we were able to move our CG back from the 25% back farther, close to the 31%, a little over 31% of the mean aerodynamic chord. So that actually gives us a lot of room. We could move that CG around, which is really good, because for this ultralight, we have a pilot in front, and pilot weights are going to change. I want to be able to handle a pilot weight range from around 110, 120 pounds up to 257 pounds. So that's going to make this CG move back and forth quite a bit. And the fuel is a little bit behind the 25% mean aerodynamic chord. So as to burn fuel, it's going to change the CG a little bit. And occasionally you want to throw some luggage in here. So I need to know how far back I can move that CG and still have a safely flying airplane. If I move that CG farther back, the closer and closer I get to that neutral point, the less static margin I have and the less safe it is to fly. Of course, if it goes past that neutral point behind it, that's completely unsafe. The airplane is unstable. It's unsafe to fly. So that deals with moving the CG behind aft of the 25% mean aerodynamic chord. Well, what about moving the CG in front of the 25% mean aerodynamic chord? And I want to be able to do that just because the wide range of pilot weights I need to be able to handle. What we need to be able to do is, as that CG moves forward, this tail is going to have to push down in order to counter that. And that's what this green arrow here is. So this is lift of the horizontal tail pushing down to counter as that CG moves forward. The farther forward it goes, the harder we're going to have to push down. But that's not the only contributing factor. The wing itself is going to try to push the nose down because it's going to have a moment. And that's what this red arrow here is representing. So with a CG in front of the 25% chord and this wing trying to pitch down just because it's inherent moment, you add those two together and the tail has to counter that. So what I want to figure out now is, with the current tail size I have and this length I have back here, is it going to be able to provide enough downforce to counter the wing moment and the CG moment? And by the way, the moment for CG is the distance from where the CG is to the 25% chord. And right here, as I have it drawn, it's 0.315 feet. And the maximum load I want to be able to handle for that CG is 580. So that includes the empty weight of the airplane and my heaviest pilot and 30 gallons of fuel. So that's what the goal of this video is. Figure out if I have enough tail here to counter all this moment here. Or you can think of it the other way around. Let's say I want to move that CG forward some distance. Now right now it's at 19% of the mean aerodynamic chord from the leading edge. Let's say I wanted to move it to 15% of the chord. How big a tail would I need in order to do that? So that's another way to look at it. Well, in order to figure all this out, we're going to have to do some calculations, a little bit of math. In fact, quite a bit of math in this one. As I was just mentioning on that picture we just looked at, we have a wing moment and we have a moment due to that CG, and we have to counter these two moments with the tail moment. So the force on the tail and its arm back behind the mean aerodynamic chord. So if you sum all these together, they should equal 0, which means you're not pitching up or pitching down. You should be in a fairly stable flight. And by convention, I should have mentioned this before, by convention, when a moment is trying to pitch the nose down, that's a negative moment. When it's trying to pitch the nose up, that's a positive moment. So both the wing moment is negative and the CG moment is negative, but the tail moment is positive. It's pushing down on the tail, which should bring the nose up, so it'd be positive. So you add those together, should get 0. Well, I know that there's two things I can calculate. I can calculate the wing moment with what we currently know, and we can calculate CG moment with what we currently know. Once we calculate those, that'll tell us what the tail moment is. So the moment for the CG, that's really, really simple. That's just the total weight of the airplane multiplied by the distance from where the CG is to the 1/4 mean aerodynamic chord. So that's what I'm saying here. Now remember, the coordinate system for airplanes conventionally is X is forward and aft. And your 0 point on X is usually going to be somewhere up close to the nose of the airplane. So the X position of the CG minus the X position of the 1/4 mean aerodynamic chord of the wing. Once you have that difference, multiplied by the total weight, that's what this W sub O is, or W sub 0. So it's a gross takeoff weight. That's 580 pounds. So you multiply that together, boom, we have that. Easy. The moment of the wing is a little harder. Now this top level equation is pretty easy. And don't forget about that playlist I have that talks about various aero terminology. This Q is dynamic pressure. This S wing is surface area of the wing, and this is the planform surface area, not the total wetted area. This C of the wing, lowercase c, that's the chord of the wing, and it's actually the mean aerodynamic chord. And this big C is the coefficient of moment. And basically that's just a measure of how hard that wing is trying to pitch down. But we're going to get a little more into it because calculating all these other things, this dynamic pressure is known, surface area of the wing is known, quarter of the wing is known. We don't know this yet. We're going to have to calculate that. That's going to be a little bit involved. Well, let's do the easy one first. Let's get the moment from that CG. Now this is just a reminder here that we're working on the moment of the CG. And again, here's the equation we just looked at on the previous page. So 580-pound pilot, that's going to be at the XCG. And as I said, that's around the 90% mean aerodynamic chord. And as I showed on the picture we were looking at previously, that distance is 0.315 feet. So 580 times that 0.315, and by the way, that's negative because it's in front of the CG. That gives us a negative moment of 182.7 foot-pounds. So that one's very easy to do, no problem. Let me talk about a couple other things where we are working to get the moment of the wing. What we want to do is figure out when the worst case is for this moment. When are we going to be producing the maximum moment? Because it's going to change in different flight conditions. So generally, that worst case is going to be when you're at your landing speed and you have full flaps. So that's our landing configuration. Because when we're having full flaps, that's when we're producing the most coefficient of moment on the wing. Actually, I should back up a little bit. That's not necessarily when we're going to be producing the most moment on the wing. The most moment on the wing would definitely be with full flaps, but would be at our maximum flap deflected speed. The speed at which the flaps can still handle the load without being torn off. So that's actually when you'd be getting the maximum moment. But the tail can also counter that. So that Q number here is going to be the same for calculating this moment as it is for calculating the down load on the tail. And we'll talk more about that here shortly. But that means they're going to basically be balancing each other. So the moment here on the wing, with this Q going up with higher speed, would be countered equally by the tail pushing down because it's going to use Q also in figuring out the downforce. So that'll kind of cancel us out. But keep in mind, that moment due to the CG is going to stay the same regardless of speed. So it's going to play a bigger role at lower speeds. So that's why we're going to be doing all of our calculations at landing speed. And by the way, that landing speed is at 24 knots for a Part 103 ultralight airplane. And that dynamic pressure we're going to calculate at that landing speed gets used over and over everywhere on design. So just actually having that handy is always a good idea because you're going to use it a lot. So from that moment equation for the wing, the only thing we don't know yet is the coefficient of moment for the wing. Now I used Dan Raymer's book, Aircraft Design, A Conceptual Approach, in order to figure out how to calculate that coefficient of moment for the wing. And this is the general equation for doing that. You take the coefficient of moment for the airfoil, multiply by your aspect ratio. If you have a sweep, that you stick that in here, and then you divide by aspect ratio plus 2 multiplied whatever the cosine of your sweep. Now, my sweep is 0, so this is going to be a 1, and this is going to be a 1, so basically they just drop out. So it boils down to the coefficient of moment for the airfoil, and this is the section coefficient of moment, which we can calculate using something like XFoil or XFLR5. Once we know the airfoil we're using, we can calculate coefficient of moment. And I've talked about that on other videos. And then we have the aspect ratio divided by aspect ratio plus 2. It's really pretty simple. And by the way, when you're working on calculating that coefficient of moment, we want to figure out what it is at the stall speed, because it does change a little bit. And we'll talk a little bit more about that here in a moment. And we want 2 different coefficient of moments. We want one for the wing with the flaps not deployed, and we want the one for when the flaps are deployed. And we'll find out why here shortly. And with XFLR5, you can calculate coefficient of moment with flaps deployed. At least plain flaps. I just noticed that I have wing suspect ratio instead of wing aspect ratios. Okay. Oh, by the way, that sweep is at the 1/4 chord of the wing. So you could have different sweeps at the leading edge, trailing edge, and at various places along the chord of the wing. So they're considering that sweep at the 1/4 chord. And here's an example of using XFLR5 for the airfoil that we're using on the UWS-4. This is the UAK02. It's based on an airfoil that a patron for the channel came up with. Thank you, Keith. So as you can see, it's fairly flat along here. This is angle of attack up here. 0 is over here on the left side. This is coefficient of moment coming down here. So it gets more negative as you come down. 0 is at the top. Now you want to make sure you do the calculation at the correct Reynolds number for your wing. So you're going to determine the Reynolds number based on your chord and the landing speed. And for the UWS-4, that's right here. It's a little over 1 million for the Reynolds number. And I happen to know that the stall angle of attack for this airfoil is around 18 degrees. So it's right up in here. So I would take this number right here and I would plug it into this equation here to get the aspect ratio for the wing when the flaps are not deployed. Now down here, we've done the same calculation, except this time it's for flaps deployed for the same airfoil. The flap chord is 25% of the wing chord. And again, Reynolds number and angle of attack. So we're stalling at about 18 degrees for most of the wing. So we come down here and we're going to grab this number, which roughly minus 0.18, although I have a more accurate number here shortly. So we would pluck at the correct Reynolds number, this yellow line. And for plain flaps, that's what we do. Now I'm going to have slotted flaps, so it's a little bit different. So now we have two coefficient of moments. We have one with flaps and one without flaps. Now how are we going to use these two to get the entire wing? Because we don't have flaps covering the entire span. Let's go take a look at that. So here's a top view of the wing. And it's just a rectangular wing. This is the center line. This is where your fuselage would be. So here would be the span of the wing. Now the flaps for the UWS-4 cover 70% of the span. Now here I'm showing the semi-span, so 1/2 of the flaps cover 70% of 1/2 of the wing. So flap here and flap here. They're split here because there's a dihedral right here, so they work together, but it'd be two sets of flaps. Aileron is out here. The aileron's going to be about 25% of the chord, and that's because this tip out here I'm going to make removable so I can put different tips to experiment with, so the aileron doesn't go all the way out. But 30% of the wing out here is going to be unflapped. Here in a moment, we're going to be looking at an equation where you're going to take a ratio of the surface area of the wing that has flaps on it, and then the total surface area of the wing. So it's going to be S sub S would be this green area, surface area of the wing that has flaps, and then S sub W, this W did not go in the right place, would be the surface area for the whole wing. I mean, you can either do whole wing or you can do semi-span wing, either way, as long as the ratio is correct. Now, if we're only interested in the coefficient of moment without flaps deployed, this equation is enough to give us exactly what we want. But we want it with our flap deployed, but our flaps aren't full span, they're only partial span. So this equation won't actually work. But there is a way to work around this issue. So I did some investigation trying to figure out how in the world can I figure out what the coefficient of moment is for a wing that has partial span flaps. In Dan Raymer's book, Aircraft Design, A Conceptual Approach, he has a method for doing it. I wasn't really comfortable using that method, partly because he doesn't use the coefficient of moment with flaps deflected, the airfoil section coefficient of moment. And I have that because I can use XFLR5. So I wanted to find a method with that coefficient of moment calculated for flaps deflected. What kind of equation can I use to come up with the answer for the whole wing? And I found an answer. And frequently, this is where I find answers. Horner has a book called Fluid Dynamic Lift. It's in its second edition. And in searching in there, I found what I wanted. Now that's on page 5-37, figure 51. Now I've kind of made a modified version of his figure. So let's talk about what we got here. Up here on this top axis, it goes from 0 to 1. This is the ratio that we were just talking about, which is the surface area of the wing that has flaps over the entire surface area. So if you have no flaps at all, you're down at 0. If you have full span flaps, you're over here at 1.0. Now the UWS-4 has 70% span flaps, so it would be right in here. Now over here on the y-axis, this is coefficient of moment, very similar to what we were just looking at for the airfoil that we're using. 0 is up here, and then you come more negative as you come down here. Now, this is the equation we were just looking at, same exact equation. This coefficient of moment is the section coefficient of moment without flaps deflected. Aspect ratio, the cosine of your sweep. So same thing. So for a wing with no flaps, like I said, we'd be over here at 0. So you plug all of our numbers in and you would get this number over here. And in fact, we're going to do this here in a moment. But what if you have full span flaps? Flaps go from the root clear out to the tip. Well, that would be out here at 1.0. Well, we're going to use the same equation that we used up here. So this is the same equation, except this coefficient here is the suction coefficient with flaps deflected. All the other numbers are the same as they were up here because the wing hasn't changed. So you run that calculation and you get this point down here. Looking at Horner's graph, which is essentially what we have here, you'll see that this is actually a straight line here. As your flap span increases, your coefficient of moment increases linearly, proportionally. So it ends up making a straight line, which makes it really, really easy. So all we need to do is plug in our surface area ratio, come down and find out what this value is, and then come over here. Well, instead of using a graph, let's just use an equation. This is just a straight line, so we'll use a line equation. So all I had to do is figure out the slope, which is basically this value here. Position along this axis is this value here, and then we add in this constant, which is this little difference here. So equation for a line. So just plugging in our ratio up here into this gives us our coefficient for the whole wing over here. So let's calculate this point here and this point down here. So here's our equation again, and we're going to plug in the coefficient of moment for our airfoil with no flaps. So that's this value here. Again, our aspect ratio is 4.5, 0 degree sweep. Plug all that in. We get a coefficient for the wing without flaps of minus 0.008. Now, what about having full flaps, full span? So now our coefficient that we're going to plug in is for flaps deflected, the section coefficient for that. So that's this number here. Everything else is the same. So we put it all in here, do our calculations, and now we have minus 0.126. But now we can use our equation that we have the two endpoints and figure out what the coefficient of moment is for 70% span flaps. So now that's the equation we were just looking at on that graph for the line. So this is going to be 0.7, and then we stick the two coefficients we just calculated into here, and we have a coefficient of moment for a wing of minus 0.0734. Well, now that we have the coefficient of moment, we can calculate the moment for the wing. And this is our moment equation here, so we just plug in all of our numbers. Dynamic pressure, 1.95, that well-known number, our surface area of the wing, the chord of the wing, and the number we just calculated, the minus 0.07 for the coefficient of moment. You plugged all that in, and we get a coefficient of moment of the wing of minus roughly 90. Well, now let's go back to some of our moments. We have the wing moment, we have the CG moment, we add these two together, so that total moment is 272. So our tail has to have a moment to counter that exactly. So our tail has to have a pitch up moment of 272 foot-pounds. So at least now we have that after all that rigmarole. So now how do we break this down? How do we get down to the surface area that we need for the tail in order to handle this moment? Well, let's take a look at the lift equation. Now this is a rearranged lift equation. Lift equation says our surface area is equal to our load divided by, again, this is our dynamic pressure, multiplied by coefficient of lift. Our load is easy to figure out. A moment is load times an arm, or force times an arm. Well, we just calculated the moment, that's 272. We know what the arm is. Let's go look at that. The arm is that distance from the quarter chord of the horizontal tail to the quarter chord of the wing. So that's 12.7. So we know the arm and we know the moment, so we can calculate this force here, this L, this load for the horizontal tail. Well, that's this equation right here. So our two moments summed together divided by that length, that 12 feet, that gives us a downward force of 21.4 pounds. So now we know what the load on the tail is. It has to push down at 21.4 pounds, at least at the stall speed, flaps deflected, and the forward CG. Okay, so let's go back to our lift equation. We now have the load, we know our dynamic pressure, and what are we going to do about the coefficient of lift of the tail? Now we're going to use Martin Holloman's book, Modern Aircraft Design. So he says use a coefficient of lift of 0.8. That's right here. So we're going to plug in our known numbers now right in here, and we'll calculate a surface area of our tail of 13.7 square feet. So we now know how big the surface area of our tail has to be to counter the moment from the forward CG and the moment of the wing. Well, let's go back and look at how big we said the tail had to be for the static margin we wanted. That was 19.5 square feet. And we just calculated for this other condition, for the forward condition, 13.7. So we're going to use whichever one's bigger, and that's going to be this one. So the one we calculated in part 13A is the one we're going to use. Oh, by the way, I should mention, in that last video, it actually was 21.9 is the value it came up with. I did a little more tweaking on my values there. I wanted to see if I can get just a little bit more static margin out of it, or I wanted to see if I could reduce the weight of the tail a little bit. I'll probably save what I did there for another video, but essentially what I did is I changed the chord of the elevator from 45% of the chord of the tail to 40%. By making that elevator smaller, it made the stabilizer bigger, which helped increase the stability. I should have mentioned in the past, it's called stick-free stability. So you're letting go of the stick so the elevator can move. By reducing the chord of that elevator, I made the stabilizer big, which doesn't move, so it increased the stability. Well, once I increased that stability, it went up to something like 8.5, almost 9. We started about 7.5. So I thought, well, heck fire, I can actually make my tail just a little bit smaller now and save some weight. So that's what I did. So then I made the overall chord a little bit smaller. Now, even though that increased the aspect ratio a little bit, which actually helps make your static margin a little bit larger, my overall surface area went down, which reduced the static margin. So eventually I was able to cut off about 5 inches of the chord. So it made the horizontal tail a little bit smaller. It's going to be a little bit lighter, and I still have the same static margin. So that worked out. So that's what I did. So that's why I went from 21.9 in that last video to 19.5. But it is bigger than the one we just calculated, so we have to go with the bigger one. There is a little more calculating in this video than a lot of them, but it's all very simple calculations. There's just a lot of them. And using a spreadsheet makes this a whole lot better. Just like in the last video where I used a spreadsheet. In this one I didn't use it, but it would be easy to do, and it would make the errors less likely to happen, and it makes it a little easier to play with stuff. Let's say you wanted to move that pilot a little bit forward so that the CG moves forward, and then your spreadsheet would immediately pop out what the updated surface area that you would need. Oh, and speaking of that, since this surface area I just calculated, this 13.7, is so small, that means I could actually move that pilot even farther forward if I want to. So at some forward point, this surface area would get big enough to actually match this. And that might be an interesting thing to calculate at some point, but I'm not going to do it now. Now, if I did that, I'd have to move the pedals forward, which would move my lightest pilot situation forward also. Lightest pilot is when I have the furthest aft CG. That would move that CG forward, which would increase my static margin also, which would then make it so I could make this surface area smaller. So that's something to think about. What's next in Dan's book on Simplified Aircraft Design for Homebuilders? Well, his next chapter talks about range and performance. Now, I'm not going to do any of this until I actually have more concrete numbers on the weight of the components of the airplane, so I can get a more detailed, more accurate CG calculation and weight calculation. Now, in range and performance, he talks about recalculating the stall speed. Well, we've been doing that all along. That's really our number one criteria in our design is stall speed. So we already know what the stall speed is going to be, or at least pretty close. I mean, we'll be able to dial it in even more after we get the accurate weight, but we're pretty close right now, I think. We could calculate the takeoff distance. I'm not going to need to know that until I have to actually have the airplane built. I'll calculate that. Rate of climb, that would be nice to know early, but not really necessary. If I'm unhappy with rate of climb, what I can always do is put in a more powerful engine and then reduce the pitch of the prop so I don't go over the 55 knot maximum level flight cruise speed. And that would give me a greater rate of climb. So I'm not worried about calculating that right now. And then the maximum speed and cruise speed. Maximum speed, I think I have a pretty good handle on that. Cruising speed, I think I have a pretty good, well, I shouldn't say I have a good handle on it, because I don't yet have a good handle on the drag. And that is always going to be an issue trying to estimate drag. Now what I can do, especially if I get a bigger engine, is I can just adjust the pitch of the propeller to get that maximum level flight cruise speed of 55 knots. And then whatever the cruise speed is what I get. Range is something I'll probably calculate after the design is done, so I don't really need to do that right now either. So really, the next thing to do is to get into the structural design of the airplane. So there will be some more videos on loads, like I need to calculate the loads that the landing gear is going to impart. I need to know the loads that the engine is going to impart. I've already got the wing loading pretty much figured out, although I do need to go back and add in some details for that, for the load from the tail being transferred through the booms into the wings. That's something that hasn't been put in there yet, so I still need to do that. So that's going to tweak that a little bit. But for the most part, that's what I need to do next. More loading and more designing of parts and testing. So at least for now, we are done with using Dan's book, Simplified Aircraft Design for Homebuilders, at least until we get the detailed design of the airplane done. So really, I guess the next video is going to be truss nose rib design testing. I have the drawings of the rib ready to go. I just need to go out in the shop and glue those down and start cutting out the forms, cutting out the ribs, and something else, I'm going to try to do some hydroforming. I bought some big rubber pieces that I can do a little attempt at some at least minor hydroforming, small part hydroforming. So that'll be a lot of fun too. So I got some learning to do there. So guys, thanks for watching. Until next time.